Right, so on to the final speaker of the session. Nice to welcome Seán, who's going to talk to us about graph theory, I think. So, yeah, over to you.
I'll do a bit of it, yeah. So, thanks everyone. Title of my talk, Graph-Based Machine Learning Models and Earth Observation Data for Social Good. So it's a bit of a broad name, but I'll explain it generally and then bring it back down. So machine learning has been increasingly used alongside EO data to monitor socioeconomic changes. Like, big one is population estimation. We've seen poverty mapping, even things like supporting COVID-19 responses in some communities. The list goes on. I could probably fill a few slides with it. But one of the challenges of the existing machine learning methods is the incorporation of spatial context. So, what's spatial context? So, it's the information from the surrounding areas that can help you understand and predict something within the area of interest. So, if we take this building, right, and I show you just a picture of this building, and I ask you, what kind of people are in here? You will come out with some guess. But then if I tell you, oh, well, it's, now I extend the picture and say, well, it's beside the School of Maths and Sciences, you'll be like, oh, maybe Maths and Science in there. So that's just adding a bit more spatial context to the idea. But how do you include spatial context for machine learning methods? Because that relationship is kind of tricky. So on the left here, you see a standard table that we'd all use for any machine learning, IDs, and then you've got features. Our idea is to add spatial context in the form of a graph. So this is Mozambique represented as a graph. And I'll explain what all those things mean in a second. Yeah, what's a graph and how do you use them? So you take a country, so Mozambique, and any country can be split into geographic units, and they can go finer and finer. You can treat those units as what we call nodes, right? So nodes in a graph. And all of those nodes will have features. And then you can have these things called relational edges, and they connect the nodes in different ways. Now, that's the beauty of it. They can connect things. You can define how they're connected. So I'll show later on different examples on how we connect those nodes. But very quickly, you could have nodes that are, if they're geographical units, they'd be touching each other, like bounding areas. Or you could have areas that are connected by railway, or nodes connected by roads. And lots of capability. So now I'm going to gently describe the idea of a graph neural network. So it's just think of it as a neural network, except it takes graphs. That's the number. If you come away with that, you're probably fine. But so you start with your graph on the left here. So that's our Mozambique graph with nodes and edges. Then we pass it into this GNN. And the magical thing about this is the message passing, right? So GNNs can capture complex spatial dependencies, both short range and long range. And they can aggregate the information from the neighboring regions, enabling kind of more insightful predictions for socioeconomic dynamics. So in this middle part, you use the GNN to let nodes share information. That's what message passing is. So in this process, each node aggregates information from its neighbors. The message passing allows the model to understand the similar regions are often connected in the context, in this, say, population density, and can form each other's patterns. So it's really helpful when data is missing in parts of the graph, because information can propagate from known to unknown regions of the graph through those learned relationships. So you do this for a number of times. You kind of do a single pass forward. The embeddings from the nodes that are multiplied by the weights, they get passed through a linear layer. You predict something. In this case, it's population density. You calculate the loss if you have the labels. Go back, do that for amount of epochs until you have a nice trained model. So, okay, I've kind of already alluded to an example task of population density. So let's predict population density across administrative areas in Mozambique using satellite-based features and then spatial relationships between those nodes. So the first step is we'll create the graph, and then the second bit is the GNN training and then the testing. So the first thing is the nodes, right? I mentioned that the nodes have node features. So I'm really lazy by nature, and going to all these sources was a pain when I had to do this for every single boundary. So what I did was I made a kind of pipeline, and actually, hopefully this is less needed now because I've heard of a few LLMs that hopefully will do this for me. But the idea is that So it kind of uses different things. It uses Stack, uses Google Earth Engine, even uses simple things like Beautiful Soup for web scraping. It goes to all these different sources and downloads the data for your country. So this kind of has nothing to do with GNNs. This is just like, if you're interested, you could use this. So all you have to do is specify your credentials for all of these sites. It's actually just 3. And then you just pass in a country, so Mozambique, and then a year, that year of whatever your data is for. And then it downloads it for the whole country. And then the last step is you pass in a shapefile. So remember I said like geographic units, the shapefile will just have boundaries. You pass all of them in, and it extracts all the features from your country's data for each of those units. And what you ended up with is a nice CSV file ready for easy use. And then this is just to bring it back to graphs. That's me using it for the Mozambique. So now at this stage I have a graph with nodes and then node features. And those node features are all Earth observational data sources of different types. So now we have a graph of nodes. Next step is the edges. So edges, they're spatial relationships. On the far, so we're looking at administrative level 3 for, zones for Mozambique, so there's lots of them. This one we call neighboring edges. So they're just if edges if boundaries are touching each other. That means they get an edge. The next edge type, we use OSM data, OpenStreetMap data, and we say, okay, let's plot all the major railways going through Mozambique. And then we can just connect, using the railway, we can connect all the nodes that that railway passes through. And the same with roads. And then the last edge, this is a bit of a tricky one to explain, hierarchical edge connections. So you have a country, the outline is admin 0. You go into that division up there, the top one, so that's admin level 1. And then you would have admin level 2, admin level 3. It's just further dividing your area into units. But so every unit should have a parent. So you can establish these parent-child relationships. So then I could look at all these admin level 3s and say, well, they're all the parent of admin level 2. And why that's important is I could have administrative data for admin 2 that's not really specific for admin level 3. So I can use the information from the admin level 2 down to the children of admin level 3. So now we've made our data. It has the nodes, it has the edges. Let's get training. So back to this. We've already talked a bit about this. Just to talk about a little bit more is, in this example, we're trying to predict on nodes for population density. So I've kind of highlighted the training nodes as blue. So you just use those nodes to learn. So this is showing one edge type, but you would do it for every edge type using a relational graph neural network. And it would basically calculate weights for every single edge type. So then all your features in all your nodes are multiplied this weight. And you get these embeddings for your nodes that contain not just the useful representation of the node features, but also the kind of contextual information, that spatial context information in the weights. So you do this for a number of epochs, you get your trained model, and then now you're ready for your testing, your inference. So all you do is you use the same graph. That's the thing. So before, these two graphs are the same. They just have two different masks in the graph object, a training mask and a testing mask. You can still use the information in training. You can use your test nodes. You're not predicting on them. You're just using their node information. So you use the same message passing as before with the weights, the same weights, and then you just predict on your new nodes here. So you've predicted density 1, predicted density 2. These are just initial results, I'll say. So what we did was we kind of split Mozambique up, honestly 50-50 in a geographic way. We have 200, so there's 566 nodes, you have 4 edge types, and then there's over 2,000 edges, and then we run that training process. So we compared it to 2 pretty powerful tree-based models. I mean, someone told me random forest will always be your second best model, which is, I don't know if that's good or bad, but we're close, which I think is good. You can see it's gotten a trend. It has learned the relationship. And again, this is just an initial attempt. We've put in these 4 edge types. Perhaps 2 of them are actually only important. Maybe the hierarchical edges aren't important. Maybe the railway edges aren't important. So It's annoying because I've gotten a lot of ideas being at this conference, so I'm eager to get back. So we're not finished with graphs. I think these are really exciting initial results, and what GNNs allow, they allow so much flexibility because we can establish more relationships, different edge types, let's get them in. And we can even say different edge weights. We could use contextual expertise to say, someone might say that, two places that touch each other, that's absolutely important. But two cities that are connected by railway that far apart, not so important. So you can incorporate a weight into that for the training. Also, we can have more nodes. Graphs do better with bigger, or GNNs do better, much better with bigger graphs. So if we got down to administrative level 4, or even 5, or even 6, more nodes, more node features, more learning. We do expect it to get much better prediction. The more node features, of course I could extend the GeoFlow pipeline. It's a very preliminary start, and I've gotten a few ideas this week of different EO sources to get in. And I'm also interested, maybe we could add in some EO foundational model embeddings. There was a paper by Google that they've released embeddings for postal states in the US. Could we use those embeddings as features with our other EO features? This point here, more generalization, that's the gravy I want. Going from semi-supervised to unsupervised. So using contrastive loss. You determine our two nodes. You're not using labels. You're determining how similar are they to each other, and then you give them a score. And by doing that contrastive loss, you can actually just create node embeddings, and then you could use them for a bunch of downstream tasks. So in that way, you'd be kind of creating a foundational model in that you could use it for things like, population density, poverty index, health risk, pollution, whatever you can think of, I suppose. That makes sense. And then, sorry, a point I forgot to mention is more dimensions. So at the minute, this is just spatial. I'm just dealing in 1 year. We could make this temporal, add the temporality part. Use the years of data to add another dimension. So yeah, there's lots to be done, and thank you very much.
Thank you very much, Sean. Any questions from the audience? Yeah.
Thank you for that super interesting talk. You started out with data collection and a sort of way of gathering data on Mozambique. Is there anything built into that process that helps you understand as you go through how accurate your country information is, and therefore how accurate your predictions might be?
I have to think about that. I would say no to start in that. I think there's a certain level of distrust, and I'm starting to get more and more untrusting of these sources because they all come from different things, and it's kind of been one of the themes we've been talking about this week. In that, for example, for I use land classification as some of the features, but ultimately they're just a product from somewhere that's been most likely trained on another country. Are those land classifications accurate for Mozambique? So I think the problem of the more you add on, the more you use that's out there, you're adding more and more uncertainty to your data. And I've not figured that bit out yet.
Yeah, Marcus.
At this point, you are primarily having a construction of your graphs based on administrative units that already are sort of predefined. They come from either cultural, partially geographic kind of features of the landscape, or the communities, etc. Is there a way to go away from that, actually using, say, urbanization-based sort of data, the kind of construction of the graph, so either at master level or landscape similarity level or something like that?
I would say absolutely you can do that. I mean, it's how we've defined the nodes are just we used administrative boundaries that we've obtained from the HDX, Humanitarian Data Exchange, but I mean, you definitely could use another way to geographically split that country.
Follow up then on that, is that in the sense in how the architecture is built? Is it static, or does the graph also, or is there a feature that the graph can evolve? So that actually the network finds the best graph, for example, to identify your pattern?
Does the graph update, as in change its node features?
Yeah.
I wouldn't say that it changes the actual feature. It learns to aggregate them in different ways. So it learns from its neighbors what features are important. I mean, this is a node classification task. With GNNs, you can do edge detection. You can even do feature, you can fill in the features for your nodes. You can do node classification. This is node regression. But the GNN should learn in its own way what's important about the graph and increase the strengths or find the importance and find out what's not important. Yeah. Sorry, I hope I answer your question.
I've got a final question, which I suppose comes from the basis that everything I know about graph theory comes from the last 10 minutes of my life. But I'm just wondering, what does this add to our capability beyond, for example, space-time geostatistics or something? Because there are already tools like variograms or, other sort of spatial analytical techniques that we can use to, I suppose, capitalise on that neighbourhood information, right, that exists within GIS or whatever. So what's the value of going to this sort of next step and using more sophisticated pipelines to do that beyond the old school geostats methods?
It's a tough question. I guess our kind of thinking was, we're aware that spatial context, of course, exists in spatial statistics. I suppose we're really just trying to see, can we do that with machine learning, and is it a better use case, or are the old methods better? I'm sorry, I need to think about that question.
That's fine. Good. Have I got time to take no more questions? Andy's saying no, so you can hold your questions for the coffee. Sorry, I know there's a lot of interest in this talk, so you might be a bit bombarded in the break, but we're going to take a break now. What time do you want people back, Andy?
10-minute break.
10 minutes. Okay, thank you. Thanks to all.